Welcome to This Explainer. Today, we're going to absolutely transform your daily support engineering workflow. If you've ever felt that sheer frustration of spending hours wrestling with a complex SQL query just to investigate a customer issue, only to end up with a messy, somewhat inaccurate report, well, you're in exactly the right place. We're going to upgrade you from writing basic, confusing reports to writing definitive, undeniable answers. And our secret weapon? SQL window functions. Honestly, this is the exact feature that separates the engineers who just pull reports from the engineers who actually solve problems.
Okay, let's dive right into this by looking at a painfully familiar scenario. A ticket comes in asking which users made their first failed transaction in the last 7 days. Sounds like a totally simple question, right? But if you've actually tried to solve this using basic select statements, a bunch of self-joins, and massive, deeply nested subqueries, you know it's an absolute nightmare. Your code becomes impossible to read, performance just completely tanks, and honestly, you're never entirely sure the data is actually right.
So let's look at why that happens by comparing group by versus window functions.
See, when you use a traditional group by, the database collapses your rows. You completely lose the individual row identity. If you group by user to find their total transactions, the specific timestamps and the transaction IDs just vanish into a single summary row. But window functions, using the over clause, do something kind of magical. They add a calculated column to your results set while preserving every single original row. So you get to retain the full context of the transaction history while still getting your aggregated metrics.
The crucial part here is the over clause. Think of it as the engine of a window function. The over clause defines the window or the specific set of rows that the function operates on. Inside it, we use partition by to divide our data into groups, kind of like grouping by user ID, but without destroying those underlying rows. Then, we use order by to define a sequence, like a chronological order by date. This basically creates an isolated, perfectly ordered timeline for every single user in your database.
Moving right along, let's talk about finding first and last events with ROW number.
Think about how the syntax works here. We call the row_number function, and then we open our over clause. We partition by user ID, which means we're creating a separate little bucket for every individual user. Then we order by created at, sorting their specific transactions from oldest to newest. What this function actually does is assign a unique sequential integer, starting right from 1, for every row inside that specific user's partition.
Imagine you've got this pulled up in your MySQL workbench. You're looking at user 101. Their first transaction on April 20th gets a row number of 1. Their next transaction on April 22nd gets a row number of 2. Make sense? But notice what happens when we hit user 102. Because of our partition by clause, that counter resets completely. So user 102's very first event gets a row number of 1. If you want to find everyone's very first event, you literally just wrap this in a common table expression and filter for where the row number equals 1. No self-joins required at all. It's beautiful, it's clean, and it's incredibly fast.
All right, next up, detecting changes with lag.
Think of your data as a literal timeline. Normally, SQL only lets you look at the current row you're evaluating. But window functions essentially give you time travel capabilities. The lag function lets you look backward to a previous row's value. Conversely, the lead function lets you look forward to the next row. This is exactly how you identify trends, drops, or breaks in a sequence without ever having to leave the context of your current row.
Here's how that breaks down. Lag takes 3 arguments. First, the column you actually want to peek at. Second, the offset, meaning how many rows back you want to look. This usually defaults to 1, looking at the immediately preceding row. And third, there's an optional default value to return if there is no previous row, like when you're at the very beginning of a user's history.
To see why this is such a game changer, imagine tracking a user's transaction status. For the very first row of user 105, the previous status is naturally null because there's nothing before it. On the second row, the current status is success, and the lag function looks back and sees the previous status was also success. But on the third row, the current status is failed, while our previous status column clearly shows success. By simply comparing these two columns in a where clause, you can instantly pinpoint the exact second a user's sequence flipped and they started experiencing errors.
Now, let's shift gears slightly and look at tracking with running totals.
This concept is absolutely vital when a client asks about their account balance or accumulated charges over a specific billing period. By placing an order by clause inside the over window for a standard sum function, we completely change its behavior. Instead of just giving us one giant grand total at the bottom, it gives us a running, cumulative sum that builds row by row chronologically.
And the magic really happens the moment the partition changes. For user 201, the running total perfectly accumulates down the rows, 100, then 150, then 350. But the exact moment we hit user 202, because of that partition by user ID, the running sum satisfyingly resets right back to 0 and starts over. So user 202 gets their own perfect, isolated balance starting at $75. It's just an incredibly elegant way to handle balances.
Okay, let's bring it all together for the final boss, a real-world support scenario.
We have all had this exact ticket lands on our queue, right? An angry client typing in all caps claiming a double charge. They're insisting the second charge happened just a few minutes after the first one. Now, as a support engineer, you can't just guess or take their word for it. You need definitive, data-backed proof of exactly when those charges occurred so you can authorize that refund escalation.
So here is the exact step-by-step workflow to solve this ticket definitively. Step 1. We set up our window, partitioning by both the user ID and the date, ordered by time. Step 2. We drop in ROW number to instantly isolate any transaction on that specific day that gets a row number of 2 or higher, because that means it's a duplicate. Step 3. We use lag to pull the timestamp of charge number 1 directly next to the timestamp of charge number 2. That lets us calculate the exact minute gap between them. And finally, step 4. We export this undeniable proof as a CSV. The resulting output is exactly what you need to attach to that JIRA ticket. You can clearly see user C99's first charge at 1400. Right below it, row number 2 flags the duplicate charge. And because we used lag, we easily generated a minute since last column, explicitly proving the second charge happened exactly 4.5 minutes after the first. Case closed, the refund is completely justified, and you did it all in one clean, row-preserving query.
So, the absolutely crucial takeaway from this explainer is that window functions aren't just some neat little SQL party trick. They are a fundamental paradigm shift in how you query relational data. I want you to mentally scan through your current library of massive, nested subquery scripts that take forever to run. Which of those frustrating, brittle queries are you going to rewrite using the elegant, row-preserving power of window functions today? Get out there and start writing answers, not just reports.